All right, so here we are with section 3.6 on rational functions. So we want to recall a rational function is a function of this form. R of x is equal to p of x divided by q of x, where p and q are both polynomials and they don't share any common factors at the moment. So meaning that you can't factor something out of the numerator and denominator and have them cancel. That'll be for later in the section. But as of right now, nothing's going to cancel out of those terms. So this is what a rational function is. I think we've mentioned it a few times that this is what a rational function looks like. But mostly we'll just call them like fractions that contain x. They're called rational functions, and this section's all about them. But so rational functions, they're made up of polynomials, but their graphs don't look anything like graphs of polynomials. They look completely different, even though they're still made up polynomials. And domains of rational functions consist of all real numbers except for those that make the denominator equal to 0. Sounds familiar? Well, at least it should, because whenever we've done domain problems and finding domain, we worked with rational functions all the time. We said that the denominator couldn't be 0, and we had to exclude those values out of the domain. Since the beginning of the semester, you've been finding domains of rational functions. So something that really shouldn't be anything new to us at this point is finding domains of these types of functions. Then we've got one of the probably 3 most classic math jokes of all time. We've got, I, the imaginary number, and pi, the irrational number. Pi is irrational because it never ends. But so pi is telling the imaginary number I to get real, and I is telling the irrational number pi to be rational. So funny. This is like in every single math person's joke arsenal ever. So common. It's so overused. But you gotta throw it in there, lighten things up. All right, moving on. We're gonna have rational functions and their asymptotes. So you've probably heard of the words asymptotes before. You probably did some sort of work with them, at some point in your mathematical career. So you probably have some like feelings or at least some knowledge of what asymptotes are. But we say that our function is undefined at specific values of x. That makes our denominator equal 0. So you had to pay special attention to the behavior of your function near those x values. So as an example, we're going to think about f of x is equal to 1 over x. And this is widely known as probably the most basic rational function of all time. It's like the most simple, 1 over x. We say that if x is approaching 0 on the negative side, f of x will start increasing in the negative direction, aka decreasing. So as you get closer and closer to x on the negative side, f of x will get closer and closer to negative infinity. So that's one very specific type of thing that we see. We say as we approach 0, and we've got this minus sign, we see this at the bottom here as well, this minus sign in the exponent's place. This means from the left. It's not a real exponent. It just means from the left. So we would say in this case, y is approaching infinity or negative infinity as x approaches 0 from the left. And we're really talking about the left-hand side, like the left-hand side of the graph. Then, very similarly, on the right-hand side, the positive side, as we approach 0, as we get really close to 0 for x, as we approach 0 from the right on the positive side, f of x gets bigger and bigger and bigger. It approaches positive infinity. So we would say that y approaches infinity as x approaches 0 from the right. And we see a plus sign in the exponent spot. So that's what those mean. They're notation, they're not real calculations or anything like that. It's just a specific type of notation. We also use it with arrow notation, which we've learned before in describing this behavior. But these are very common behaviors that we see towards any values of x that you've excluded from your domain. Those values of x are called vertical asymptotes. We're going to have the definition for it in a few slides here. But those are called vertical asymptotes. Your function, as it approaches a vertical asymptote, only has two options. It's going to positive infinity or negative infinity. And those are the only options that your function has. But so here's a summary of the notation that we have here, just running through it really fast. Highly encourage you to pause, copy all this down. But we've got x approaches a from the left, the minus sign in the exponent spot means from the left. X approaches a from the right, the plus sign is in the exponent spot. Then we've got x approaches negative infinity or decreases without any bounds, and x approaches positive infinity or increases without any bounds. This is all using arrow notation. So highly encourage you to pause and copy this down if you haven't already. So moving on, we say, given this previous example, f of x is equal to 1 over x, the same thing we looked at that other slide, we see that something also happens. We said that when x approaches this number 0, the vertical asymptote that our function can't exist at. Now we want to think about, well, what happens when x becomes large in the positive or negative direction? So what happens when x goes towards positive or negative infinity? And we see that f of x will get closer and closer to the value of 0. So we've got some charts here just to kind of show us this behavior. We see as x is getting larger in the negative direction, or as it's decreasing, it's approaching negative infinity, f of x is going to get closer and closer to 0. We're not going to say what side or anything because it's just approaching 0. Then we see as x increases, gets larger as it approaches infinity, f of x will also still get closer to 0. So we see in both cases, f of x approaches 0 as x approaches negative or positive infinity. And this is a picture of the graph of f of x is equal to 1 over x. We see it's got this very distinctive shape to it. And rational functions have these very distinctive shapes. We see, this is the vertical asymptote. Our functions are not crossing it, and they're going to positive or negative as they approach. So we see, f of x goes to infinity as x approaches 0 on the right-hand side. Then x approaches 0 on the left-hand side. F of x goes to negative infinity. We see that over here. And then we've got the ends, kind of end behavior, really. F of x is going to approach 0 as x goes to positive infinity, and f of x goes to 0 as x approaches negative infinity. So we see that kind of end behavior here. But our function hugs the axes. It's really hugging the vertical asymptote and the horizontal asymptote. Just so happens that these are on the axes. But your function will hug your asymptotes, and they'll be kind of across from each other a lot of the time. So that's the very distinctive type of graph that we see for rational functions. If it just so happens that you want to try and reason out whether your function's approaching infinity or 0 at a given value of x, you can base this on the following reasoning, and this is for positive real numbers. But if you have 1 over a really, really big number, like basically infinity, you're going to end up with some really small number that's basically 0. So that's what's happening as we see this here. But that's not what happens, a little bit later on. 1 over some small number will give us a really big number. If we're dividing by some number that is just super close to 0, we're basically going to positive or negative infinity. So that's kind of the reasoning that we can have if we want to know where our function is going for, say, close to 0 or infinity. And here is the actual definition of vertical and horizontal asymptotes. So for the vertical asymptote, we say the line x equals a is a vertical asymptote of the function y is equal to f of x if y approaches positive or negative infinity as x approaches a from the left or from the right. So we're seeing that these vertical asymptotes, they go up or down, these, dotted lines here. Our function can only have two options. It's going to negative infinity or positive infinity on either side of the vertical asymptote. Those are the only options for your function. And vertical asymptotes, you can imagine, are hard boundaries. Your function cannot cross a vertical asymptote at any point because it's not even defined at that value. So your function cannot cross a vertical asymptote. Instead, it swerves. It either swerves up going to infinity or it swerves down going to negative infinity. And we see these two pictures here to the left. We're thinking about our function from the right-hand side. So these are, approaching a from the right. And on the right-hand side, should have flipped these. On the right-hand side, we see that these functions are going towards our asymptote, towards this value of a from the left. They're from the left-hand side of the graph. And they're going to positive or negative infinity. Then we have horizontal asymptotes. So we see the line y equals b as a horizontal asymptote of the function. Y is equal to f of x, it's a typical function. If y approaches b as x approaches positive or negative infinity. So these two pictures kind of represent horizontal asymptotes, and two kinds for that matter. We see that on this first one, y approaches this value of b as x approaches infinity. As we go towards infinity, our function approaches this value. But we also see y approaches b as x goes to negative infinity. We've only defined this statement for negative infinity. So this is what matters over here, because then we see our function goes and crosses right through that horizontal asymptote. Your horizontal asymptote is like a soft boundary. Your function can cross through it really anytime. But we should see that it's really more like end behavior. It's going to describe what our function is doing towards positive or negative infinity, not anywhere in the center or anywhere on the side where it's like not defined or anything like that. So horizontal asymptotes are asymptotes that exist side to side. We're saying as x approaches positive or negative infinity. This is end behavior of your function. And vertical asymptotes, these are up or down. Your function cannot cross it. It has to go to positive or negative infinity. So these are the two types of asymptotes that we're going to be looking at first here. So we're going to go ahead and do our example. We don't need to use any notes or anything. We're just going to kind of talk it out and reason it out, and we'll finish it off after this example here. So example 1, we state the horizontal and vertical asymptote of the function. F of x is equal to 1 over 2x plus 4. This is our function. That's great, but this is what it looks like on its graph. Remember, you're not graphing rational functions on your homework or anything. You're just identifying correct things like where horizontal and vertical asymptotes are. So looking at our function here, if we want to find the vertical asymptote, we need to find the value of x, where if we drew an imaginary line going up and down, our function will obviously not be crossing it. And we see that happening at one very specific spot on this graph. If we draw a dotted line here at x equals -2, our function will never cross. It's going to get really close, but it will never cross. This means our vertical asymptote is x equals -2. Then you also want to think about the horizontal asymptote. So we want to look for the value of y side to side that our function looks like it's not crossing, especially just mostly towards the ends. And if we're looking, it looks like our function is not going to cross, well, the x-axis. That is the same thing as saying y equals to 0. So our function is not going to cross the value y equals 0, which means that y equals 0 is our horizontal asymptote. So we see this function hugs the asymptotes there that we see. And they look like they, are across from each other too as well.
All right, so that was example 1. So let's go ahead and move on to our next topic here, which is going to be transformations of y is equal to 1 over x. So a rational function of the form f of x is equal to ax plus b divided by cx plus d can be graphed by shifting, stretching, and or reflecting your graph of f of x is equal to 1 over x using the transformations of functions that we learned from section 2.6. So in section 2.6, we learned all the different types of transformations of graphs. And so graphs of 1 over x can be used in this sense as well, to shift, stretch, reflect that graph, depending on what types of transformations that you've made to your function. So it works in a lot of the same senses. If you add or subtract values, to x or to your entire function, you will shift. If you multiply any values to either x or the entire function, depending on the value of that number, that can be a stretch or a shrink of your graph. Or if you are adding in any negatives anywhere, that would be a reflection of your graph. And in this case, it's always going to be the graph of 1 over x that you are making these transformations on. We saw that the rational function of 1 over x is that very classic type of rational function. And so those are kinds of transformations that we're going to make on them. So we see all the different types of transformations here. So shifting is adding or subtracting a number either to the function entirely or just to x directly. Reflecting is adding a negative to x or the entire function. Stretching and shrinking comes from multiplying a value. Depending on whether it is greater than 1 or between 0 and 1, it may be a vertical stretch or shrink or a horizontal shrink or stretch, depending on those values. So if you want to brush up on those, definitely feel free to look back into section 2.6 at those different types of transformations. And then there is just a few problems on your homework that relate to things like this. So I just want to be familiar with those types of transformations, and you should see very similar transformations being made on the graph of 1 over x. So moving on to the next and more important topic, we have asymptotes of a rational function. So we just looked at some vertical asymptotes. So we're going to be looking at really both vertical and horizontal now. So the rational functions we've looked at so far have been relatively simple. And so now we're going to work with more complicated rational functions. Since rational functions are a polynomial divided by another polynomial, we've seen how big and large and crazy messy that polynomials can really get. So they can be a lot more difficult rational functions instead of the ones we've seen so far, which have been like 1 over x minus 2, and things like that. So finding asymptotes of a rational function, we say lowercase r here is a rational function, and the rational function r of x is equal to a polynomial divided by another polynomial. And we normally say that polynomials have this very specific look to them, where we have something like a sub n times x to the power of n plus a sub n minus 1 times x to the power of n minus 1, all the way down until we get to a sub 1x plus a sub 0. So it's a very typical function where we see decreasing exponential order, and all of these a sub n's or a sub n minus 1s, these are all going to be the coefficients of x. So this is just indicating one polynomial divided by another. We see that in the denominator, it's very similar. The only thing that changes is that we go from an a to a b and an n to an m. They mean the same thing. We just use different notations to indicate that these will be different polynomials, most likely. I think in every case, they will be different polynomials. I don't think you'll ever encounter the exact same one. But yes, this is what we will see here. One polynomial divided by another. So for finding a vertical asymptote, these are going to be the lines, or line a, or x equals a, so the value of a, where a is some 0 of the denominator. So we saw that before with example 1 of a vertical asymptote. You would take your denominator, set it equal to 0, solve for x, and those are the values where you have vertical asymptotes. So it all depends on the denominator. If this sounds very familiar, that is because we did the same thing with finding domain. When it came to finding domain of a rational function, you take the denominator, you set it not equal to 0, and that will tell you what x cannot be. This is the same idea because a vertical asymptote breaks the domain. So this is why we had to do that, and this is kind of the reasoning behind it. So it's because they were always caused by a vertical asymptote. So we find vertical asymptotes the same way that we would find domain of a rational function. Take your denominator, set it equal to 0, solve for x, and there are your vertical asymptotes. Then for finding a horizontal asymptote, you would do it using one of the three cases. So it's cases, it's not steps. So there's only three cases, and so we're going to use the letters N and M indicated by the exponents on X. So N is the highest exponent in the numerator on X, and M is the highest exponent on X in the denominator. So we're saying that N is the degree of the numerator and M is the degree of the denominator. So if N is less than M, meaning that the degree of the numerator is less than the degree of the denominator, R would have a horizontal asymptote at y equals 0. And that's the answer. So as long as the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is just y equals 0 every time. And we're going to skip to the third case, and then we'll talk about the second case. So in the third case, if n is greater than m, meaning that the degree of the numerator is bigger than the degree of the denominator, then your rational function doesn't even have a horizontal asymptote, doesn't have one at all. Then we have this middle case. If they are equal, meaning that if the degree of the numerator is equal to the degree of the denominator, then your horizontal asymptote occurs at y equals a sub n divided by b sub m. So we notice that a sub n is the coefficient in front of the leading x term here. So x to the power of n, we have a sub n, and b sub m is the leading coefficient of the denominator. So you would divide these two values, and that would be the value of the horizontal asymptote. So when finding a vertical asymptote, same idea as domain, set the denominator equal to 0, solve for x. For finding a horizontal asymptote, you have one of these three cases. And every single problem you encounter will be one of the three cases, and you just have to know what to do for which one. If it's case A or C, they're very straightforward. You just have to determine which is greater. Step B has one extra step, but it's not that much more complicated. So let's go ahead and do an example where we have to use that second case. So case B. So example 2, we're going to find the horizontal asymptote, our rational function r of x, where r of x is equal to 3x squared minus 2x minus 1 divided by 2x squared plus 3x minus 2. So let's go ahead and go to our notes so we can do this problem together. All right, so here we have our rational function. It's equal to 3x squared minus 2x minus 1 divided by 2x squared plus 3x minus 2. And we want to determine the horizontal asymptote. And the horizontal asymptote really depends on the degree of the numerator and the degree of the denominator, which, if we remember, the degree of the numerator is the highest numbered exponent. So the degree of the numerator in our case here is 2. That's the highest numbered exponent. Then the degree of the denominator is going to be the same. So the degree of the numerator is equal to the degree of the denominator. The highest numbered exponent is both 2. This indicates that n is equal to m. So it's that second case on our last slide. And we know that if n is equal to m, then y is equal to a sub n divided by b sub m. So that was what we saw before. This is telling us that that the horizontal asymptote is going to be the coefficients divided by each other. So if we can recognize that the degree of the numerator is equal to the degree of the denominator, like we just said here, what we're going to look for is the numbers in front of the x, in our case, x squared. In our case, it's 3 over 2. And we can kind of circle them like this. You can even highlight them. 3 over 2. So the coefficients are 3 and 2. You divide them. You're basically just going to take that chunk, and that's a horizontal asymptote. So the horizontal asymptote is y is equal to 3/2. There you have it. You can rewrite this if you like. If you don't like fractions, you can also say, y is equal to 1.5. That's fine as well. But that's the answer. Horizontal asymptote is y is equal to 3/2, 1.5. You don't have to put it in decimal. And honestly, it's easiest to keep it as a fraction since it's already kind of in that form that you already see there. So there you go. Horizontal asymptote, y is equal to 3/2. So when it comes to horizontal asymptote, it's really just picking out which one's right. So it's important to know like the degree of the numerator and degree of the denominator, what that means, and what the different cases are. So if you know what the different cases are, it's pretty easy to tell what the horizontal asymptote is going to be. So, all right, let's go ahead and go back to our lecture. All right, so that was example 2. Moving forward, we have graphing irrational functions. So section 3.6 is a little bit of that melding between the algebraic side and the graphing side, because in the beginning of chapter 3 we had a lot of graphing, then we kind of moved into more of the algebra. This is really going to be both. This is algebra plus the graphing. So graphing a rational function. Guidelines, we have 5 kind of steps here. So our guidelines are number 1, factor the numerator and the denominator if possible. If it's not possible, don't force it. But if you can, you definitely want to try to factor your numerator and denominator as much as possible. Step 2 is finding the intercepts. So you want to find the x-intercepts by determining the zeros of the numerator and the y-intercept from the value of the function when x equals 0. Then step 3, find the vertical asymptotes or vertical asymptote if there's just one. So your vertical asymptotes, find the vertical asymptotes by determining the zeros of the denominator. Then you want to see whether y is going to go to infinity or negative infinity on each side of the vertical asymptote by using some test values. Step 4, horizontal asymptote. You're going to find the horizontal asymptote, if any, using the method previously described. So looking at the cases and whatnot. Step 5, you're going to sketch the graph. So graph the information provided by the first 4 steps. Plot as many additional points as you would need to fill in the rest of the graph of the function. So these are all of our steps. These are steps we're going to go ahead and take to graph a rational function from example 3. So example 3, we're going to graph the function, then we're going to also state its domain and its range. So we have our function here, r of x is equal to 5x plus 21 divided by x squared plus 10x plus 25. So we're going to go ahead and we're going to work this problem out in our notes. All right, so here we are with problem 2. We have our rational function 5x plus 21 divided by x squared plus 10x plus 25. So like we said from our last slide there, our very first step that we're going to do is see if we can factor anything. So if we look at our function here, our numerator is 5x plus 21. It's not really a whole lot to work with. The only coefficients that we have, or the values that we have, are 5 and 21, and 21 is definitely not, divisible by 5, so we're not going to factor it. There's no way to really factor it in any nice way. We'd only end up with probably some really ugly numbers, and we don't want to deal with that. So our numerator is not going to be factored. But we can look to the denominator. And the denominator is x squared plus 10x plus 25. And if we look at that, and we see, maybe I can do some reverse FOILing. I can figure out, 2 numbers that when multiplied together, they equal 25. And when they add together, they equal 10. And at that point, I should think, I know a number like that. That is 5. So we see that x squared plus 10x plus 25, that's one of our perfect squares that we kind of went over in one of our last sections there. So it's a perfect square. We see that x squared plus 10x plus 25 is going to be the same thing as x plus 5 squared. So we can go ahead and factor that. And we can just rewrite it in its other form. So you got 5x plus 21 divided by x plus 5 squared. So having it in this factored form is going to make it that much easier for us to find some of the other things that we're supposed to be finding, like things like the vertical asymptote and stuff like that. So having it factored makes it easier, which is why we want to factor it. But we want to keep both forms here, just so we can look at them. And if we need them at any point, we can grab them pretty easily. So you don't want to like erase the original or anything. But we have both forms here. This is the expanded versus the factored form. So this is factored form. And this is the expanded form. All right. So we've got our two forms here. We factored it. That was step one. Step two is we want to find the intercepts. So let's go ahead and let's start with finding the x-intercept. Your x-intercept is wherever your function is equal to 0. And one thing that can be pretty nice about finding an x-intercept in a function like this is that your denominator can be anything except 0. You never want the denominator equal to 0. That's where the vertical asymptote is. But other than that, it doesn't matter what your denominator is. As long as your numerator is equal to 0, your function is 0. So if we're finding an x-intercept, you want to know when is my numerator equal to 0. So vertical asymptotes are when the denominator is equal to 0. X-intercepts are when your numerator is equal to 0. So for the x-intercept, we'll have the numerator equal to 0. Our numerator was 5x plus 21 is equal to 0. We're going to solve for x. We're going to go ahead. We're going to subtract 21 from both sides. We get 5x is equal to negative 21. Divide by 5 on both sides. And we get x is equal to negative 21 over 5. Great. Cool. So now that we know this, we have our x-intercept. Now we can find our y-intercept. So the y-intercept, in this case, is found by plugging in 0 for x, and then finding what r of x is equal to. So you're going to let x equal 0, and whatever is left over. So we're going to have 5 times 0 minus 21 plus 21, not minus, there we go. And then 0 squared plus 10 times 0 plus 25. So 5 times 0 is 0, plus 21 is 21. 0 squared is 0, plus 10 times 0, which is 0. So 0 plus 0 is 0, plus 25 is 25. And then we have it. There's our y-intercept. So the y-intercept is going to be 21 divided by 25. So there's some things that are going to be helpful to us later. So we've got x, we've got y for all those intercepts. Now another really easy way to find the y-intercept is that your y-intercept is the constants at the end. So we see that when we were finding horizontal asymptotes, we compare the degrees of the values of x, or the leading coefficients. With the y-intercepts, it's going to be the two constant values at the end in the same format of the rational function. So we would have 21 over 25. These numbers right here for the y-intercept. So it's just a quick little way, if you remember, to find a y-intercept of a rational function, quite a bit faster than any other problem. I also just realized that this says problem 2. This should have been problem 3. There we go. Not problem 2. But anyhow, quick way to find the y-intercept. You can do that as well instead of plugging in 0. You'll still get the right answer either way. That's up to you. So, all right, we found the x-intercept and the y-intercept, which is great. Now our next step is the vertical asymptote. So to find the vertical asymptote, we know we want to set the denominator equal to 0 and solve for x. So our denominator is x squared plus 10x plus 25. But we also know it's x plus 5 squared. And x plus 5 squared is a lot easier to work with, so that's what we're going to use. We've got x plus 5 squared is equal to 0. We want to get rid of the squared part, so you can take the square root of both sides. Which, when you do that, the square root of x plus 5 squared is just going to be x plus 5. and square root of 0 is just 0. X plus 5 is equal to 0. Solve for x, subtract 5 from both sides. You get that x is equal to negative 5. So there is a vertical asymptote at x equals negative 5. All right, this is working out nice. All right, then we want to find the horizontal asymptote as well. So the horizontal asymptote, remember, this is going to be found by comparing the degrees of the numerator by the degree of the denominator. So if we look at the numerator, we have 5x. X by itself indicates x, whoop, wrong one, indicates x to the power of 1. So we have 5x to the power of 1 over x squared. So comparing the x terms here, we see that the degree of the numerator is less than the degree of the denominator. 1 is less than 2. So for our horizontal asymptote here, we have that n is less than m, which if you remember indicates that there is a horizontal asymptote at y is equal to 0. So if the degree of the numerator is less than the degree of the denominator, y is equal to 0. If they're equal, you divide the coefficients. If the degree of the numerator is greater than the degree of the denominator, then you don't have a horizontal asymptote. So let's go ahead and just write that next to it. So degree of the numerator is less than the degree of the denominator. Just barely fit that in there. All right, so that's what that statement is, the n less than m. That's what we're saying. Degree of the numerator was 1, degree of the denominator was 2. So there we go. So those were our steps. Now really the last thing is just to graph the function. And we also, before we graph the function, we do want to do one other thing. We want to know the behavior of our graph near the vertical asymptote. So we want to determine that before we move on and graph it. I jumped the gun a little bit there. But we want to find the behavior of the function near the vertical asymptote. So we're going to go ahead and we're going to write that out. So behavior near the asymptote. So the behavior near the asymptote, we're going to separate this into a few separate things here. So we have as x approaches the vertical asymptote, then we have that the sine of y is blank, we'll fill that in. That means so y approaches blank. So we're going to fill in these statements here. So that first column there is kind of just what we're labeling this. And then we're saying that x is approaching the value of the vertical asymptote. The value of the vertical asymptote is -5. And you always want to look at that value from the left and from the right. So we're saying as x approaches -5, first from the left. So we want to know from the left, is it going to go to negative or positive infinity? Also, we want to check on the right as well. So this is from the left. This is from the right. And so we're going to go ahead and we're going to fill this out. We want to know what the sine of y is going to be. Because if the sine of y, when you're incredibly close to -5 from the left, meaning that you're just slightly like less than -5, less in the negative sense, so -5.0001 is kind of what we're considering. Then for the right, this would be something like -4.99999 kind of thing. So those are the values that you should be thinking of. Anything along those lines? We're just thinking very close to -5 from either side of that value. So if we think of those numbers, while we kind of wrap this up here, we want to look at, is my numerator negative? Is my denominator negative or positive? What's going on? What is the final kind of sign going to be here? And if we look at our function, we see that our denominator is squared, which means that it doesn't matter what value we plug in for x. Since it's squared, it will always be positive. So our denominator is always positive. So we go down here, we're going to kind of make a little bit of just a slightly kind of theoretical statement here. We're saying that our function is always being divided by a positive number in both of these cases. And we see our little rational function there. There's a little fraction. And we're going to put something in the top here. We want to know, is the numerator going to be positive or negative? Because that's going to determine if the sign of y is positive or negative. So we could by all means plug in negative 5.000001 or negative 4.99999 in for x into the numerator. But what we're going to see are these numbers are so incredibly close to negative 5. If you just plugged in negative 5, 5 times negative 5 is negative 25. And negative 25 plus 21 is somewhere around negative 4. So the closer that you're getting to negative 5, the closer you're getting to the value of negative 25, which either way just means that your value is negative. It's going to be incredibly close to negative 4 either way. And we don't care about the value, we care about the sign. So the sign of y in both of these cases, since the numerator would end up being negative, the sign of y would be negative in both of those cases. So once again, it doesn't matter what the value is. It matters what the sign is, because we know that the denominator is always going to be positive because it's squared. So if the numerator is negative in both those cases, then we see that the sign of y is negative, which means that since y has to go to positive or negative infinity as you approach that value of negative 5, that means that they're both going to negative infinity. So that is kind of how we determine this. We say that y is going to go to negative infinity as x approaches negative 5 from both sides. So we see that when we draw a vertical asymptote, each side of that graph should be going down to negative infinity as it comes closer and closer to that vertical asymptote there. The vertical asymptote is like a brick wall. You're going to swerve around it. You're not going to go right through it. You're going to try to swerve around it as much as you can. So they're both going to go to negative infinity. So we have quite a few bits of information here. From a rational function, we know what our x-intercept is. We know what our y-intercept is. We know what our vertical asymptote is going to be. We know what our horizontal asymptote is going to be. And we know the behavior of our graph near the asymptote. Now that we know all these things, it's great. If we tried to graph our function right now, it'd be a little tough. We would probably know around, the right way we should be graphing this, but we don't know 100%. So we're going to go ahead, we're going to draw out our coordinate plane, and then we're going to see what we really need. So let's go ahead. I'm going to draw out the coordinate plane. I'm going to put all the information on the coordinate plane so you can see what this is going to look like. All right, so here's our coordinate plane with all the information that we've kind of gathered here, all plotted on the same coordinate plane. We see that we have the x-intercept, the y-intercept, the vertical asymptote, the horizontal asymptote, and we know that our graph here is going to go to negative infinity on either side of the vertical asymptote. So we see that our graph, our function is going to be coming like down this way on either side. We don't know exactly what it looks like yet. That's just an example of what we know it's probably going to look like. But we really don't know the rest of the function. We really have no idea what we're kind of looking for and what it should look like. we can probably make a guess, but that doesn't mean that our guess is necessarily going to be right. Another thing we know is that towards the edges of the graph, toward the left and the right, our graph will be kind of adhering to the horizontal asymptote as well. So they'll be coming up really close to the horizontal asymptote, but never touching. But when it comes to the horizontal asymptote, it doesn't necessarily matter in the middle. If your vertical asymptote is like a brick wall, your horizontal asymptote is like a very, very poorly built wooden fence. You can go through it if you like, but only in the center. So your function can cross a horizontal asymptote in the center, but it should be adhering towards the edges, since we see that's kind of that long-term effect of the horizontal asymptote. It tends towards the horizontal asymptote, towards negative or positive infinity, but it really doesn't matter in the center of the graph. So at those edges, towards the edge of the graph, it will be coming up to the horizontal asymptote, but in the center, it doesn't matter. It can cross the horizontal asymptote, and it's really not a big deal. We see that it will, be more affected towards the edge. But the point is, we don't have enough information. We're looking at our graph. We don't have enough information to fill in kind of what the graph is going to look like. Also, the question asks to find the domain and the range of the function. We don't really know. I mean, we can find the domain, but the range would be really tough at this point. So what we're going to do is we're going to pick some example points, and we're going to go ahead and we're going to write those out. And so we're going to have a bunch of points to pick from when we fill in these values. And because I have done this problem before, I will fill you in on what these points need to look like. So I will give you the table. So the x values we're going to pick here, we're going to go ahead, we're going to write it kind of down here. So we're going to pull our function down a little bit. And we're going to put it over here, say x and r of x. So we're going to pick a bunch of values of x, and then we're going to calculate r of x. The values we're going to pick for x, we're going to pick, we want a good, spread here. We're going to pick -10, -3, -1, 0. Oh, we already have 0. That's the y-intercept, so we don't necessarily need 0. 3, 5, and 10. So those are the range of values that we're going to use here, just to get a really kind of good look at what's going on. So we can go ahead and we can fill these values into our function. So what you'd be doing at this point is you'd be plugging in these values of x into r of x. So you'd be plugging these values of x into your function to see what your function is equal to. So that's what you're going to be doing. And just for time's sake, I'm going to go ahead and I'm going to fill the values in with what they need to be. And I hope that you'd be able to do this on your own by just plugging in those values into your function for r of x to find new values. All right, so these are the corresponding r of x values for all the values of x. Now, notice I did add 2 more values of x in there. I realized that it wasn't enough points. It's always okay to realize at some point. If you realize, like, hey, I don't have enough points here, I don't have a good accurate representation, and just add some more. So I did add 2 more values. I added -6 and -4 as well. So we have a spread from -10 to +10, but we have -10, -6, -4, -3, -1, 3, 5, 10. And so we have all these calculated values as well. So when x is -10, r of x is -1.2. When x is -6, r of x is -9. When x is -4, r of x is 1. When x is -3, r of x is 1.5. When x is -1, r of x is 1 as well. When x is 3, r of x is 0.6. When x is 5, r of x is 0.5. And when x is 10, r of x is 0.3. Whew, that's a lot. So we're going to plot all of these points on here. We're going to erase the lines that we drew earlier. We know that that is where our graph should be heading. So we see that these points should reflect that. So if we go ahead and plot these points, we're just going to estimate. I mean, obviously, this is a hand-drawn graph anyway, so we are going to be estimating these values as best as we can. All right, when x is -10, we're going to have -1.2. So it's probably going to be somewhere around here. Then we see when x is -6, we have -9. which if you notice, the y-axis is kind of very close together. So that -9, we're just going to imagine that it's going to be like down here. It's going to be a lot farther than that, but we're going to get the idea here with our graph. So our y-axis could only plot so much. If I made it any larger or like any more squished together, it would be very hard to see. So I had to do it like this. So 6 is -9. We're getting that idea there that it's going down to negative infinity. Then when x is -4, we have 1. -4, we have 1, which is over here. Then we have -3 is going to be 1.5. So even up here. And then -1 and 1. Right about there. Then we have 3 and 0.6, 5, 0.5, 10, 0.3. All right, so we've got some extra points here. We know our graph should be going down to negative infinity as we approach the vertical asymptote, so we can kind of make an assumption what our graph is going to look like. We assume from this point on, our graph is going to be coming down like this. So if we connect our points, they're going above, we see our function is going to kind of start looking like this. It's coming down to the vertical or the horizontal asymptote. And then on the left-hand side, we've got this point here. We see it's kind of going to come down this way and going to go up that way. So we had to kind of fiddle with that one just a little bit. This would keep going, obviously, down there. So this is roughly what our graph is going to look like. Now we're going to go ahead, we're going to go to Desmos, and we're going to compare our drawn graph with a perfect graph on Desmos. So let's go ahead and go to Desmos and see what our values are going to be there. All right, so here is our graph on Desmos, so the perfect, really nice graph that we're kind of looking at here. We can fill in our vertical asymptote. We can say, x equals -5. We see a line drawn there. You can click on that and you can play around with that if you'd like. You can make it like a dashed line or a dotted line. So you can have that like nice kind of vertical asymptote there. So this is how we kind of drew our graph in our notes. But obviously, if we kind of zoom out a little bit, we get a much more clear picture of what this graph is looking like. So we definitely see that our function is going to negative infinity on either side of that vertical asymptote that we see there. And we also see that towards the edges of our graph, we see that our graphs are definitely adhering to that horizontal asymptote at y equals 0. You can fill that in as well if you would like. So same thing there. You can change that to a dashed line. You can have those in there. We can see that our rational function is adhering to those values. So the graph that we drew was not bad, but it definitely wasn't perfect. It wasn't ideal. So when it comes to functions like these, it is always best to have a graphing device and graph them. That will always give you the best values and everything, especially when it's going to come to things like range. Domain, we can find even algebraically, we don't need a graph for that, but for finding the range, we will need to graph a function to find that value. Because even when we picked values, we got that, when x was -3, y was 1.5. And that's pretty good. But if we were to round this value, this is really 1.6 or even just 1.563 as it is. So we were close, but we were not, right on the money. And it would have been very difficult to find this maximum value. So it's very difficult to do that algebraically. You have to do that by graphing, and it would be really hard to just find that value by hand. So it was really important to kind of graph functions like these when you have questions like this, just so you get a very accurate representation of that rational function. So, all right, here's what our graph looks like. We see that along the x-axis, all our values totally work except for x equals -5, or vertical asymptote. And our range, we see that we're coming, from negative infinity, we're coming up. and this is our highest value, 1.563. So our range would be from negative infinity to 1.563, and our domain would be negative infinity to -5, union -5 to infinity. So we're going to go ahead, go back to our notes so we can go ahead and write that. All right, so our domain, like I said before, it's being broken off by the vertical asymptote. So our domain is negative infinity to -5, union -5 to infinity. So we have those two separate chunks there. And our range, this was really found by using Desmos, like we just saw before. We see that we are definitely starting at negative infinity, and we're going to come up to 1.563. And that value does get included, so we want to make sure to put a square bracket on that. Whenever you're talking about range, you're going to put a bracket. Whenever you're talking about domain and these types of functions, it will be parentheses. So, all right, there is our domain and range. This was our great attempt at graphing this function. And then we found all this other information. Oop, that meant to be the highlighter. There we go. And we found all this other information from our graph. So that is how you graph a rational function, or, roughly graph a rational function using the information that you can kind of pull just from the equation itself. So, all right, let's go ahead and go back on over to our lecture so we can continue on. All right, so that was example 3. Moving forward, we have another type of asymptote. So we also have slant asymptotes as well. If r of x is a rational function in which the degree of the numerator is exactly 1 more than the degree of the denominator, you would actually use the division algorithm to express your function in the form of r of x is equal to ax plus b plus the remainder divided by the quotient. So this is what we're going to see here. So this ax plus b, this is really the mx plus b part. So if your numerator is exactly 1 degree higher than the denominator, your answer is going to be in the answer of a linear function with potentially a remainder. So that's what you're going to see when this happens. So when you divide them, which is what you're going to have to do, you're going to have to use long or synthetic division to divide them. And this would make it so that your function comes out to ax plus b, the mx plus b part, plus the remainder divided by the quotient. So here we have that the degree of r is going to be less than the degree of q. And so a is not equal to 0. We just have to say that a is not equal to 0. This means that when x approaches positive or negative infinity, this statement is going to go to 0. Because we see that capital R of x, this degree would be obviously less than q of x. So because of that, if x goes to infinity, q of x would be going to infinity a lot faster than r of x. So it would be outpacing r of x so much so that it would be getting closer and closer to 0, the larger or smaller in the negative sense, like those numbers got. So that means that r of x over q of x would end up going to 0. So for any large values of x, lowercase r of x would really just be the line mx plus b, because this term at the end here essentially just wouldn't matter anymore. So in this case, we say that the line y equals mx plus b or ax plus b is a slant asymptote or an oblique asymptote. So all this is saying is that to find a slant asymptote, your numerator has to be exactly 1 degree higher than your denominator. If this is the case, you have a slant asymptote. You don't have a horizontal asymptote in that case, because we said that if the degree of the numerator is higher than the degree of the denominator, you do not have a horizontal asymptote. If it's exactly 1 greater, you have a slant asymptote instead. If you know or recognize that you have a slant asymptote, the way that you would find it is by using long division or synthetic division. So you can have your rewritten rational function look more like this form. And the slant asymptote is the mx plus b part. This part does not matter. It only matters this chunk right here, the ax plus b or mx plus b part. And that would be the slant asymptote in that case. So that's going to be how we find a slant asymptote and really what it means and things like that. the asymptote slant, it's a line, so that's why it's called the slant asymptote. So we're going to go ahead and find one. So example 4, we're going to find the slant asymptote and the vertical asymptote of the following function, just because. So we have r of x is equal to x squared plus 5x divided by x minus 1. So let's go ahead and go over to our notes so we can work out this problem. All right, so example 4, we have r of x is equal to x squared plus 5x divided by x minus 1. So let's go ahead, let's start off with the easier one. Let's go ahead and do the vertical asymptote. So if we want to find the vertical asymptote, remember it is the denominator set equal to 0. So our denominator in this case is x minus 1. We want to solve for x. We'll add 1 to both sides. And x equals 1. So we have a vertical asymptote at x equals 1. That was an easy one. So let's go ahead and do the slant asymptote now. So like I said before, the slant asymptote occurs when the degree of the numerator is exactly 1 degree more than the denominator, which in this case, it is. The degree of the numerator is 2, while the degree of the denominator is 1. So it's exactly 1 greater. If you're being asked to find the slant asymptote, you don't really need to verify that it's true. If it's asking you to find one, there is one. So, all right, we will find the slant asymptote by using long division or synthetic division in our problem here. So we notice our denominator is x minus 1. And we said that when it comes to dividing out polynomials, if your denominator or your divisor is x plus or minus a number, you can use synthetic division. If it's not, you can't. But in this case, we can do either one. And so that means that whichever one that you like better is the one that you're going to use. I prefer the synthetic division if it's available, and so that's what I'm going to go ahead and do. But if you want to use long division, you should come out to the exact same answer. So all right, we're going to use synthetic division. To divide x squared plus 5x by x minus 1 in order to get the slant asymptote. So if we're going to use synthetic division, we are going to set up our upside down house. We're going to fill in the coefficients of our numerator. So we have 1 x squared plus 5x, and there's no term at the end, which means that it's a 0. So we're going to have 1, 5, and 0. So we fill in our house or our upside down house here, and the number that goes on the outside of the upside down house is the value of c. Remember we said that our denominator should look like x plus or minus c, and if it's x minus c, then we just put that number directly on the outside of our upside down house. So if we look at our denominator here, we should have x minus c. So in this case, this means that c for us is positive 1. Remember, you could also set that statement equal to 0 and solve for x, which in this case, it's going to be the vertical asymptote. It's the value of the vertical asymptote. That's what happens when you set your denominator equal to 0 and you solve for x. So c is 1. There we go. So we have 1. That's our value of c. We draw that extra line underneath our upside down house there to indicate the middle and bottom row. Then we can get started. Woo! Go through the past. All right. So our first step when using synthetic division is that you want to copy down the first term. Every single time. You always want to start with that. So you copy the very first term. Oh my gosh, my screen is flying away. You want to copy down the very first term into the bottom row. Then you're going to multiply your value of c by that value in the bottom row and write your result in the middle row. So we have 1 times 1 is equal to 1. And you're going to add the column. So 5 plus 1 is 6. And we start again. The value of c times that number in the bottom row. So 1 times 6. Write the result in the middle row. and you add the column. So 0 plus 6 is 6. And then we go, we're done. So now we just need to interpret our results. The number at the end is always the remainder. This is R of X. So we have the remainder, and this is our mx plus b part. So we have 6 and 1, or 1 and 6. And remember, you determine what the remainder is, and then you tack on an x to the power of something, starting from the right, going to the left. And it always starts at x to the power of 0. So this is x to the power of 0, x to the power of 1, which this is equal to x plus 6. So, and this is the part of our quotient here. So really, since we're supposed to be putting our slant asymptote in the form of the division algorithm, our slant asymptote is going to be, let's put some colons instead. There you go. Y is equal to x plus 6 divided by x minus 1. It's by the divisor. I think I might have said the quotient before, but this is by the divisor. So this is our slant asymptote as of right now. Remember, as x approaches infinity, positive or negative, 6 over x minus 1 is going to go to 0. So it really doesn't matter. The slant asymptote is y is equal to x plus 6. And we don't care about the end part. It's just the x plus 6. So this is our slant asymptote. Y is equal to x plus 6. Because remember, your slant asymptote is a straight line. You don't want to add anything on it that's going to make it not a straight line. So since it's a straight line, we want to, remember that, keep that. So y is equal to x plus 6. All right. So that wraps up example 4. We found the slant asymptote and the vertical asymptote. So we can go ahead. If you'd like, you can always look at this on Desmos. So we're going to go ahead and do that really fast before we go back to our lecture. We're just going to take a little peek. We're going to see what this function looks like on Desmos and then compare this with our slant and vertical asymptotes that we found. All right, so here's our function x squared plus 5x divided by x minus 1. We said we had a vertical asymptote at x equals 1 and our slant asymptote at y equals x plus 6. So we can get a really good look at this. We see that our asymptote is definitely slanted. It's a line. So we see it's slanted. We see our graph here in red is really adhering to those vertical asymptotes. Even if they weren't there, our graph would still look like that. So we see that those graphs definitely adhering to those asymptotes, which means that we did this problem correctly, and this is correct. So it's always nice to look at the graph of the function, just to make sure it's correct. And also you can kind of get a feel of what slant and vertical asymptotes tend to look like when you have different types of functions. So this is what a slant asymptote would end up looking like. So, all right, let's go ahead and go back to our lecture. So that was example 4, and moving on, there we go. We have common factors in rational functions. So this is our last little topic here. So we're going to look at different ways that we can kind of graph rational functions and ways that they can look kind of different depending on what types of functions that we have. So every function that we looked at so far for rational functions have been on the simpler side, or even if they're more difficult, there's no way to really simplify. You can always factor, but it's not like things are canceling out. This is where things cancel out. So we have common factors in rational functions. So we've been under the impression that the numerator and denominator of a rational function really don't have any factors in common. But if they do, you're able to cancel that factor out of the function, just as you would any other time. And if you cancel that function, you can cancel the function for the values of x where the factor is not 0. So it's this idea that when you cancel out factors, you're able to graph a much simpler function because you're able to cancel out a bunch of terms and all you're left with is, say, x squared. Then that's really nice. You could just graph x squared. That's a fairly simple function to graph. But the caveat to that is that you're allowed to do it, but not for any values that made the factor that you canceled out equal 0. Because remember, if you're canceling it out, that factor existed in the numerator and in the denominator, and your denominator can never be equal to 0. So if that factor that you're canceling was originally in the denominator, that means that for whatever values of x that had, that made your function undefined. It would have been a vertical asymptote. But instead you got to cancel it out. But you don't get out like quite scot-free. You would put a hole in your graph at that value. So since a rational function would not actually be defined at those values of x if you had left it, the graph would have a hole at that point. So we have two examples here. Our first one, part A, we see that s of x is equal to x minus 3 divided by x squared minus 3x. We see if we had canceled out an x in the denominator, x minus 3 would have canceled in both terms. S of x would have been equal to 1 over x. But in the denominator, you canceled out x minus 3. So 3 would have originally been where a vertical asymptote existed. So you get to graph 1 over x, which is a simpler function, but then at the value of x equals 3, you have to draw a hole. And you would say that your function is s of x is equal to 1 over x for when x is not 3. So it totally looks like that graph except for that value. Same thing below for part B here, we have t of x is equal to x cubed minus 2x squared divided by x minus 2. So we could factor out an x squared out of the numerator, and we could cancel x minus 2. That would leave us with graphing x squared, which is a nice graph. So t of x is equal to x squared, but not when x is 2, because that's when your denominator originally would have been equal to 0, and you would have had a vertical asymptote there. So your function would just not be defined for that 1x value. But you could graph the nice, easy function that you had left over after you canceled things out. So that's what happens when you are able to cancel factors in a rational function. It does make it really nice and easier to graph that resulting function because the graph is probably going to be significantly easier, but then you do have to account for where you would have had vertical asymptotes. And you do that by putting a hole there instead of drawing a normal graph. So, all right. Let's go ahead and do an example with this. So example 5, we're going to graph the following function. S of x is equal to x to the power of 4 plus x cubed divided by x plus 1. So let's go ahead and go over to our notes so we can do this problem. All right, so s of x is equal to x to the power of 4 plus x cubed divided by x plus 1. So first thing we notice, there's a lot of x's in that numerator. So we can cancel out or we can factor out an x to the power of 3. That's what we can take out of both terms in the numerator. So we can simplify this to be, actually we're going to leave our color in black here. We're going to simplify this to be x to the power of 3 times x plus 1 divided by x plus 1. Hey, look at that. We can cancel out an x plus 1 for both the numerator and the denominator. And that means that our results was x to the power of 3. So we're going to graph x to the power of 3. But we have to remember where our denominator would have been equal to 0, or just where the factor we canceled out would have been equal to 0. So we graph x to the power of 3, but since we've factored out x plus 1, we have to have a hole at that value set equal to 0. So you want to solve for x in this case, subtract 1 from both sides, at x equals -1. So you're going to have a whole at this value. So you're going to have a whole at x equals -1, but you still get to graph x cubed, which we can go ahead and we can draw up a little hand graph of x cubed here. So just a really quick one, you want to make sure to have some good values here. So we've got 1, 2, 3, 4, 5. That's actually probably all we need, so we don't necessarily need to go much farther than that since these graphs are going to go very kind of long, not sideways. So 1, 2, 3, 4, 5. Draw it again there. And then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's pretty good. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is x and y. 2, 4, -2, -4. We want to graph, plug in all these values. Normally, I just pause the video when I do this, but this one was pretty quick. So drew up our coordinate plane. We want to draw up our function as well. It's x to the power of 3. It goes through the origin. It has a point at 1, 1, 2, and 8. -1, -1, and -2, -8. There we go. Those values are correct there. So we can go ahead, we can plot all those points. And there's our graph of x to the power of 3. So we have x to the power of 3. Remember, the one thing is that we have a whole at x equals -1. So where x was equal to -1, we would erase that value right there. And we would draw just a big hole instead. And there it is. There's our whole at x equals -1. So that's what our graph would end up looking like. So when you do problems like these, you want to be able to pull out that common factor. You cancel that common factor out. You figure out what you're actually going to graph. Then you figure out where you're going to have your hole at. So you take the factor that you canceled, set it equal to 0, solve for x. Then you graph that kind of more simpler function there. And then you just make sure to draw a big circle or a big hole where the hole goes. So just before we kind of end here, we're going to look at this really quick on Desmos because we will see this reflected in Desmos as well. So let's go ahead and go over to Desmos to take a look at this really fast. All right, so here's our function, x to the power of 4 plus x to the power of 3 divided by x to the power x plus 1. So we see this function graphed here. If we take that off and graph x to the power of 3, it is the same. We see it's the same one. So we know that it's going to be the same because we can factor and can cancel out these terms. But if we look at x to the power of 3, we can take this point, we can kind of drag it along. We see that, we've got all these values. And right here at -1, we have -1, -1. That's what happens when you plug in -1 into x to the power of 3. So we have all these defined values when we look at the graph of x to the power of 3. But if we look at the graph of x to the power of 4 plus x to the power of 3 divided by x plus 1, we can do the same thing, but we're going to catch something right here at -1. Look, it's undefined. So we do have a hole there. We see there's literally even a hole there. When you look at the point versus any other value, it turns into an open circle right there at -1. So it is undefined at -1, even if it doesn't look like it to the naked eye. You will have to track, a value to kind of find it if you're looking at it on Desmos. But we do see that at -1, it is undefined because the denominator originally would have excluded the value of -1, but since it, factors really nicely and it really just boils down to x to the power of 3, we see that undefined point there. So something you can find on Desmos as well. So, all right, let's go ahead and go back over onto our lecture. All right, that was example 5, our last example. So in summary, in section 3.6, we covered rational functions, transformations of y is equal to 1 over x, asymptotes in rational functions, graphing rational functions, common factors in rational functions, and lastly, slant asymptotes. Switch some stuff a little bit around there, but you get the point. All right, that wraps up section 3.6, and I'll see you again in the next one.